students, as a part of video lecture series, here is a third lecture continuing with the subject VLSI technology having subject code 053 KEC 053, and I am faculty Sangeeta Mangesh from Department of Electronics and Communication Engineering, JSS Academy of Technical Education, Noida. In today's lecture, we are going to study the significance of different processes, those are involved in the analysis or wafer preparation process. Secondly, we are going to identify the parameters based on which we define the quality of wafers. The learning outcomes, what I am expecting to gain out of this particular lecture include discussion on the, like you should be able to explain all the processes which are involved in cutting, lapping, polishing and other whatever are involved in the wafer preparation. You should be able to identify the parameters based on which wafers are, the quality of the wafers is defined, and how you go about measuring that quality, that also you should be able to find out. Then let us first check out. That day we have already seen the crystal growth process, and this crystal growth process in the second lecture we have seen using Jokralski crystal growth and float zone crystal growth. And from sand we first prepared metal grade silicon, we pulverized it, then we prepared electron grade silicon, crushed electron grade silicon was molten into the chamber, and then we prepared the single crystal. After that single crystal, whatever are the unit processes involved or whatever are the stages involved, those stages we are going to see one by one, right from grinding, slicing, polishing, all those stages have equal importance in the wafer preparation process, and therefore, we need to focus each and every stage. Each and every stage has its own significance, each and every stage has its own importance and role to play in the wafer preparation stage, okay, as a process as a whole. So, let us first check out what is this particular process. So, first thing is the stage 1, that is wafer shaping. Now, you have got the ingot. These days we are able to get ingot as heavy as 300 kgs and the diameter can go up to 300 mm. That means, you can have diameter of 30 centimeter for that ingot, and that ingot will be prepared as heavy as 300 kgs, or you can have bigger size ingots also. Now, it is simply like a wooden log what you are getting. Now, this wooden log similar to your sawmill, what we grind from the side, we remove these scales which are available on the wood. Similarly, here also we want to grind the edges so that the ingot is properly cylindrical in shape. Now, the grinding is carefully done. Grinding is carefully done using this diamond cup wheel. It is a specialized tool which is being used, and this tool ensures that the grinding is uniformly done throughout the ingot as a whole. This grinding has significant role to play because it is deciding factor as far as your diameter, final diameter of the wafer is concerned. Now, when you decide this diameter, that is exactly based on whatever is the grinding shape you obtain and how much is the total width of that log is going to be. So, similarly, here also we need to know. Not only that, apart from grinding, you have demarcation mark or identification marks also made on this particular ingot when this grinding process is happening. Now, what are those identification marks? We are going to see afterwards, but just like your LED, when you buy LED, you must have seen when you look from the top, you have a chiseled nose. So, similar like chiseled portion, and you find out that as the cathode. So, similarly, here also you just have the demarcation or primary and secondary flats made on the wafer, so that just by visual inspection you can find out whether the wafer is of N type or P type and what is the orientation of the crystal or crystal orientation of that wafer is, that also. So, we will see that in the last slide. I am going to show you that also. Now, this is basically a grinding process. Now, this grinding has to be uniform. Of course, there is going to be some loss at this point of time, because of grinding there will be some elimination of the edges. Now, one more thing you have to remember, that beveling is also equally important, because silicon during like formation of the ingot, if there are stacking faults, there is every possibility. It is a brittle substance, we have seen it is a delicate substance, that is one of the drawback of it. But then there can be a possibility of chirping, or there can be possibility of cracking, edge cracking, or any other like cracks which are because of the orientation of the crystals. Now, that you need to avoid. So, therefore, there is a lot of precaution to be taken while handling this grinding process. So, all chirping, cracking, that has to be avoided, and you need to take lot of precaution in grinding. So, this is about grinding. Once grinding is done, your ingot is properly made or flat marks are made, then it goes for the next step, and that next step is, now here your ingot is ready. It is the end from where the seed crystal was connected, and the end from where it is being pulled, those edges we have chopped off. We have made first it as a circular, like we have made it like fixed up its diameter, then we have made something known as flat. This flat surface is basically used for identification. Now, what is this identification? We will see. This identification, you will have one primary flat and one secondary flat, and depending upon the position of those flats, your wafer will be identified. Post these grinding process and making your wood log, just like your wood log of wood made proper circular, now it is the time to cut it into pieces. Now, when you want to cut it into the pieces, earlier method from almost when VLSI technology originated till very recent, this inner diameter saw was being used. Now, this inner diameter saw was basically cutting the wafers into uniform shapes, like uniform slices, just like we chop any banana or something like that. You have chopping, but the thing is, you have this particular thing done to be very precisely, because you need to have uniform surface, the area, the substrate has to be properly flat, and therefore, there is lot of precision involved. But over a period of time, since the demand was increasing day by day, and cutting these with internal diameter was not like degrading basically or decreasing the yield, the losses which are incurred, like just like your wooden what you call dust comes out of the wooden what you call cutting process. You must have all have seen ki when you cut the wood, you have something known as wooden dust flowing all around. Similarly, here also you have something known as silicon, loss of silicon, or silicon particles will be coming out, or silicon dust will be coming out, and those losses which are incurred, or the silicon which is lost because of the cutting process, we call them as kerf losses. These are called as kerf losses, and these kerf losses are responsible for loss in the yield also, and we do not want those losses to get incurred, or do not want those losses to happen, and therefore, what do? We try to minimize those losses, and that was the process which, like, there was one of the new technique which was being used, and this new technique is using multiple wires. Now, you are having multiple fine wires which are simultaneously cutting the ingot. Now, when the ingot is being cut like this, you have these wires which are cutting the ingot simultaneously. You can have 3 ingots. 3 ingots can be simultaneously cut, and the ingot size can go as big as 300 millimeter. That means 30 centimeter diameter ingot can be at a time cut, and multiple such ingots can be placed onto the cutting tool, and that is how the efficiency of overall cutting process or slicing process is increased. Now, this is what is the latest technology which is being used for large scale manufacturing when the demand of silicon wafer is increasing day by day. And therefore, this is the latest technology where multiple wires are used or wire cutting tools are used, and because of that you have lot of advantages which are available or a lot of significance, a lot of importance being why these people are preferring this, because there is a lot of significance to this method, and the significance lies in minimizing the kerf losses. Not only that, the substrate surface what we get is much superior as compared to what we get in the inner diameter cutting saw. So, rather than using saw, we are using a wire to cut those ingots. Now, once we got the ingots of uniform size simultaneously cut, these are the first stage in which we are getting the wafers. Now, these are the wafers what we are going to get after the now after this you have got slices available with you. As per the diameter of the ingot, you will have different diameter, like if you have your ingot of 30, like I told you 30 centimeter diameter or 12 inches, you can say 12 inches, like 100 mm diameter, you have the slices of 100 diameter ready. Now, those slices might not be properly uniform on the substrate. So, for that reason we do the lapping. Now, what is this lapping? Lapping is a basically the definition, as per literal definition of lapping, is an abrasive machining process. It is an abrasive machining process used to obtain materials with high dimensional accuracy and excellent surface finish. Now, this is nothing but normally whenever we try to do or soften the surface, you try to dip it into some slurry or some material and then coat it with something. So, similarly, this is also one of the process where we are putting, we are placing the wafers onto these stands which are already, basically you are having plates. These plates are holding your individual wafers. Individual wafers are then there is something known as, there will be some flow of some material which will work as a lubricant, or which will be in which your basically that material is silica, made up of silica basically, and that material will be again it will be aluminum oxide slurry, and that material will be basically we are trying to dip those wafers and coat those wafers. हिंदी में जिसे लिपना कहते हैं, लिपना, जैसे आप लिपते हो कोई चीज़ सॉफन करने के लिए. So, similarly here also we are doing the same process, we are trying to put or immerse that, and that is how we are. Now, this process has got specific features. It's in this process you do not have much of the losses of the silicon as a whole. Secondly, there is no excess of heat generation. So, there is no damage because of the heating. Thirdly, you do not have large force being applied, slowly it is being done. Now, this is just abrasive rolling will be done, and this is just to prevent any additional. Now, one more thing is your surface may not be exactly flat, there can be some, this is your wafer. Now, this wafer when you have, if it does not have exactly proper surface, then it may not be giving you proper results, and for that reason we dip it and we try to make it as flat as possible. Not only that, please understand, your wafer is never straight. Whenever you chop it, your surface is not plain, and in order to make it proper, make it clear, make it even, we carry out this particular process. The significance of this process is to make surface uniform, clear, clean, and having proper orientation, proper way. Even if there are minor dislocations, minor what you call any irregularities, those also will be automatically covered up, or those also will get automatically removed. So, this is what is the process which is called lapping. So, minor abrasive materials. Now, these abrasive materials can be varying from polycrystalline diamond to you have got silicon carbide, or multiple materials can be used for this particular process, and this process is also exhaustively studied, and for different applications, if the material or wafer is very brittle, then you tend to use less abrasive material. If the wafer is, like in case of silicon, you normally go for this aluminum oxide slurry, which is used as a material for lapping. Now, once the lapping is done, पोत के हमारी वेफर तैयार हो गई. उसका सबस्ट्रेट ठीक हो गया, हाथ काट पीट के हमने उसको लीप दिया पूरा अच्छे से. नाउ वी आर गोइंग अहेड विद द नेक्स्ट स्टेज. नाउ नेक्स्ट स्टेज इज द पॉलिशिंग स्टेज. नाउ व्हाट इज दिस पॉलिशिंग? ओके, वंस वी हैव डन लैपिंग, लैपिंग होने के बाद, नाउ वंस लैपिंग इज ओवर, वी आर गोइंग अहेड विद द नेक्स्ट. You have lot of material which is available onto the silicon, you need to clean it, and to clean it before going for polishing, we don't want any contamination onto the wafer, and therefore we go for etching. Now this etching is a very limited period etching, because you don't want the wafer to come in contact with chemicals at high temperature or for longer duration. So we normally use, okay, you use normally normal alkali solution or acidic solution to dissolve all the impurities which are so far while handling the machines, like so far while handling the wafers that have incurred into, like that have come in like when the wafer has come in contact with so many processes, there can be some impurities which have entered into, like got into the wafer, and that is why we need to eliminate them. Now not only that, whatever, okay, after lapping the wafers are always etched by nitric acid and dissolved in acetic acid or sodium hydroxide to remove the microscopic cracks and the surface damages which are available. This acid basically, okay, the acid or the caustic solution again is removed by deionized water and RO water. So always whenever you handle any chemical, post chemical exposure, always DI water is essential. So DI water, and okay, you always use DI water and clean the wafer, or you use RO water. Okay, RO water is used always. Now with this RO water or DI water, you will clean the wafer, and then wafer is ready for next process. Now what is this next process? So next process is our polishing. After lapping, we have cleaned the wafer, and now it has entered into polishing stage. Now polishing is an essential part in the wafer preparation, because every wafer is having mirror shine polish. Now this is basically done on a polishing pad, with the polishing pad. Now here you are having a mounting table or a polishing table on which the wafers are mounted. The wafers, after mounting, there will be proper pressure, its proper calculation being done, lot of mathematics has gone into it, lot of research has gone into it, and post that the overall technique has been developed. And with that you will have, see, you can have two-way polishing also, single way polishing also. These days, since the technology has much advanced, now we have gone for, now you many times prefer double sided polishing, because it is simplifying the task, though it is an expensive affair, you have lot of precautions, additional measures to be taken, but it is always recommended. Okay. These days people normally, in all the industry standards, you normally go for this kind of double sided polishing. Now what is being done over here? Now the wafers are placed on the polishing pad, there is continuous slurry which is working as a lubricant. It is just like आप जब फर्श का पॉलिश करते हो, just like when you are polishing your floor, you are putting some slurry of calcium carbonate on it, and that polishing machine revolves. So similarly here also, these are the polishing pads which rotate without creating abrasions onto the surface. Lapping has already with lapping you are having some coating onto it. So same thing is being used over here. So that is preventing any abrasions over here, and with appropriate pressure, appropriate temperature, without elevating temperature, this polishing is taking place. These polishing pads rotate, strike, okay. There is continuous wafer is facing down, you are having this particular wafer carrier, okay. This is wafer carrier, and you are continuously it is rotating, and with high RPM the polishing process continues. This during this polishing you are using silica powder. Now, what happens, even if there are minor abrasions or something like that, that will also get filled and automatically your substrate will be completely polished, uniformly polished. Uniformity will be there onto the. There are many problems which normally are encountered, especially when you have large diameter wafers. Those problems are because during the what you call process, we are going to see them in the next slide. I have already listed them out, we will see them also. But then to avoid those problems, this polishing has to be done very precisely, very carefully, and it is one of the most important stage in wafer preparation. Now, the important thing is our wafer is never having sharp edges. The wafer is never having sharp edges. We call them as beveling. Beveling means always you will never have the right angle this one. So, always the edge will be like this. It will not have a sharp edge which is 90-degree wala. See, it will not have 90-degree wala sharp edge. It will be beveled. It is called beveling, or it is also known as chamfering, CHEMFERING. This is what is the this is what is the process which is known as. Now, these are the two techniques, these are the things which are to be remembered always, and that is how your polished edge will be not at right angle, it will not be sharp, it will be beveled, and then the polishing will make, because of the rotating, because of the slurry, your polishing will end up into a shining wafer with uniform surface, perfect surface, without any inclination, without any cracking of the edges, without any irregularities. So, this is what is the polishing. Once polishing is done, cleaning. So, cleaning also though happens after every stage. We have seen cleaning once prior to our lapping, etching के बाद, like post etching we did etching after the lapping, and that time also we cleaned our wafer, and now also we are cleaning the wafer. Generally it is called as RCA cleaning, and it is performed in 3 stages. Now, what are those 3 stages? First stage is known as SC1 stage, and this is the first stage. Now, this first stage, under this first stage we use ammonia, hydrogen peroxide combined with DI water, deionized water or RO water. Now, this will remove the impurities and particles from the wafer surface. What kind of impurities? All the organic impurities will react with ammonium hydrogen peroxide and ammonia and will get eliminated. In the second stage of cleaning, we eliminate natural oxides and metal impurities with hydrofluoric acid. In the third stage, that is called as SC2, this is my SC1, this is called SC1, and I call this as SC2. Now, this SC2 and the overall cleaning process is normally called as RCA cleaning. It was invented in that company, that is why the company has given 40 years back it has been invented, and that is why the company has patented it, it has given its own name to the process, and that is why it is called RCA cleaning. Now, this process ends up in the third stage by cleaning with the solution of hydrochloric acid and hydrogen peroxide. Now, this will remove, this will remove all the oxide impurities or natural, this will grow natural oxides on this surface, it will create natural coating of oxide onto the surface, and whatever other impurities are, those will be automatically eliminated, and your wafer is ready for inspection. Now, why do you need inspection? Why do you need inspection? What all things can go wrong when you are handling the wafer? So, very first thing you can have is during crystal preparation you can have impurities because of the irregularity in the heating gradient, some material like contamination in the furnace, anything can go wrong and that can land up into impurity. Secondly, we saw slicing. When slicing, the shape can turn, there can be, okay, I told you chamfered parts can be, like when you are chipping, that time also your edges can go wrong, that time also your defects can get incurred into your substrate or wafer. Then you have lapping. Lapping may you can have waviness of the wafer, then you something we call it bow, then we call it something, okay. So, you have some variations may happen into the wafer. So, those variations you do not want. So, you need to inspect the wafer properly. Etching surfaces, you like while etching surface, if you do, if those metal impurities or those chemical impurities are not eliminated, that also can end up or that also can create some pits onto the surface. So, that also you need to. So, here you need to check out all these things, nanotopography, micro roughnesses, slurry residues, water stains. Then you while cleaning also you can have residual particles onto the wafer. So, all these things are very important, and prior to packaging into hermetically sealed packages, you must inspect these wafers properly. Apart from it, some chemical what you call electrical properties are also identified. So, this is what is the summary. Initially we got the single crystal ingot, then we made it into, first we have done the grinding, then we have converted or made its slices, then we lapped the wafer to flatten the edges, then okay, faces are parallel, then we carried out etching, wet etching, then wet etching ke baad we have carried out polishing, and then we have gone for final wet clean. Now, your wafer is ready, you want to market it, but you need to whenever you are marketing something, you must know what are the best characteristics or what are the best features it is having, or what is the factor that is deciding the quality of my wafer. And these are the basic important things which are deciding the quality of the wafer. First is the flatness, second is micro roughness, how much is the oxygen contained, what are the crystal defects, what are the particle presence available onto the, are there any particles available, and what is the bulk resistivity. And these characteristics, these parameters can be evaluated based on different things or different what you call processes, different techniques which are available. Now, what are those techniques? One by one we will see. Now, wafer testing can be carried out using electron beam probing technique, and one of the electron beam probing technique is use of transmission electron microscope. Now, this electron microscope will give you exact pattern of the orientation of the atoms, because you are focusing the beam of nanometer, okay, for and that nanometer size particle this thing imaging will be automatically magnified and placed on the fluorescent screen. You will be able to visibly see that thing and you can find out everything. Second is your X-ray diffraction topography, you can use laser probing techniques, you can use crystal impurity testing, you can use spectrography or spectroscopy, then you can use ion excitation source where you are using electron probe microanalyzer. This microanalyzer can give you all the secondary ions, idea about the secondary ions, and you will get exactly structure, what exactly is the structure inside. The crystal defects such as oxide stacking defects, oxide impurities, all or edge locations, line locations, all those things can be identified using X-ray or Fourier transform, okay, Fourier transform infrareds, FITR we call it, and X-ray diffractions, this one. Everything will give you particle size, what all type of particles are available. You can map it with the existing lookup table, you can say everything, whatever data available, and you can, whatever you get diffraction pattern you get, you can map and find out what kind of orientation the crystal is having, what kind of impurity the surface is, and based on that you decide the parameters and define the quality of wafer. So, before we go, I assured you that the flatness or the primary and secondary flats are the important things which are to be which are basically giving you help, or they are aiding you to identify the wafer, what type of wafer it is. You know already for BJT you are using 111. In case of BJT, P type wafer is having only primary flat, whereas in N type you are having primary and secondary at 45 degree. whereas in case of 100, this p type is having 90° orientation with primary and secondary flat. Primary flat is larger flat, secondary flat is smaller flat, whereas in case of your n type 100, which is used for MOS devices normally, this we use for BJT, we have seen it in the last lecture itself. So, this is being used here, we are having the flats at 180° apart. So, before we end, if you are able to answer these questions, so what are those answers we are looking for? We are looking for if you are able to describe each of the unit processor, each of the processes, that is wafer grinding, if you are able to find out what exactly is being done in grinding, what is the purpose of grinding, if you are able to define what is wafer slicing, why you need to do that, what are the precautions which are being done, what is the wafer cutting tool being used. Then if you are able to find out what is the wafer polishing process being done, how slurry is being done, how the rotation speed is adjusted. Then if you are able to find out the parameters such as micro roughness, substrate properties, then sheet resistance, like we have seen. The sheet resistance is also very important. In the previous slide I have already shown you, you are using 4 probes. Between 2 probes you are having constant current and other we have voltage, you know the properties and distance between them. So, sheet resistance can be calculated from 4-point probe method. So, these are the different techniques, different methods for identifying the electrical characteristics. Based on these electrical characteristics, if you are able to find out different parameters and identify how they are to be measured, if you are able to identify the crystal primary and secondary flats, this is okay, we have attained our purpose and this is what we are going to put an end to this particular lecture. If you are thorough with this, we will go for the next lecture, which is giving you complete idea on the cleaning technologies, wafer cleaning technologies. So, thank you, good luck and God bless.